Welcome to the deep dive. Today we're digging into the materials that actually build our world.
Yeah, from wood-based boards to, complex plastics.
Exactly. We'll be looking at what they're made of, their properties, maybe some surprising uses. We've got some good sources lined up.
hmm
The goal is really just to get a clearer picture of these everyday materials, things you might not normally think twice about.
Absolutely. It's funny how common they are. But the science and the specific reasons why one is used over another, that's where it gets interesting.
Ready to jump in?
Let's do it.
Okay, so boards first. Plywood seems like a good starting point. Simple layers of wood, right?
Well, yes and no. It is thin layers, veneers glued together. But the clever bit is the grain direction.
Ah, right. They alternate it.
Exactly. Often rotated, like up to 90 degrees between layers.
And that's for strength.
Yeah, precisely. It makes it much stronger in all directions, less likely to split. Plus, you can get good strength from relatively thin sheets. It's quite efficient.
Right. It overcomes wood's natural limitations. Sort of. Smart.
It really is.
Okay, then what about laminated boards? Similar idea.
Kinda. The source says they're thin layers bonded together, so yes, layering is key.
But maybe not the grain rotation thing.
Doesn't specifically mention it. So probably similar principal layers for strength, but maybe without that specific cross-graining that gives plywood its particular resistance to warping and splitting.
Got it. Okay. Next up. Hardboard. Or HDF. High-density fiberboard. Sounds, well, dense.
It is. This is where we get more into engineered wood. Think Isorel or Masonite. Those are just brand names for it.
So how's it made?
Basically, they take wood, break it right down into the fibers.
Like really fine fibers.
Yeah, super fine.
Yeah.
Then they mix it with binders and compress it under heat and pressure.
Ah, okay. So you get a very uniform, dense sheet, no knots or grain variations.
Exactly. Much more consistent than solid wood or even plywood in some ways.
Interesting. Now, completely different, it seems, is foam core, foam board. That stuff's super light.
Oh, yeah. Totally different application usually. Presentations, mounting photos.
Right. I've used it for that.
Its lightness comes from the polystyrene foam in the metal, and it just has paper facings, white or brown paper.
So the source calls it paper-faced foam board.
Yep. Which makes sense. It's definitely not for heavy construction, more for display, crafts, that kind of thing.
Definitely not load-bearing. Okay, back to the heavyweights. Cement board. That sounds tough. Cement and fibers.
It really is. Very durable. The cement gives it that hardness and water resistance, and the fibers stop it from cracking easily.
Makes sense. Where would you typically use it?
Well, think tile backing, especially in bathrooms, showers, places that get wet.
Ah, okay. Instead of drywall.
Exactly. It won't break down with moisture like regular gypsum board can.
Mm.
Also used as a base for exterior stucco sometimes. It's just got better impact resistance.
And I saw something about it being bendable sometimes. Polymer modified?
Yeah, that's a neat development.
Yeah.
Thinner versions with polymers added can actually curve a bit.
Wow. For what, like curved walls or something?
Precisely. Archways, rounded corners. It allows for designs that would be really hard with rigid sheets. Still needs support, though.
Still, bendable cement. Okay, next. Gypsum wallboard, which most of us just call drywall, right?
Right. Drywall, plasterboard, wallboard. Lots of names for it.
The standard for inside walls and ceilings.
Pretty much, yeah. It's basically gypsum, the calcium sulfate dihydrate stuff pressed between sheets of paper.
Just paper.
Well, special facer and backer paper. It's relatively easy to install, gives a smooth finish for paint, and importantly, it's fire resistant.
Oh, because of the gypsum itself.
Yeah, there's water chemically bound in the gypsum crystals. When it gets hot, that water turns to steam, which helps slow down the fire.
Huh. Didn't know that. Okay, last board. MDF. Medium density fiberboard. Another engineered one.
Yep. Similar process to hardboard, in some ways breaking down wood into fibers.
Using a defibrator, it says.
Yeah, that's the machine often used. Then mixed with wax and a resin binder, pressed with heat.
So how is it different from hardboard then? The density.
Exactly. The name gives it away. It's denser than plywood and definitely denser and stronger than particle board, but it's less dense than hardboard, HDF.
So it fits in the middle of the fiberboard family.
Pretty much. And it really took off in the 80s, apparently.
Mm-hmm.
Used a lot in furniture, cabinets, shelving, places where you want a smooth, stable panel.
Right. Okay, that's a good tour of the boards. Quite a range.
Definitely. From layered wood to reconstituted fibers.
So let's shift over to plastics now. What's the basic definition we're working with?
The source says they're synthetic or semi-synthetic organic compounds. The key thing is that they're malleable.
Meaning they can be shaped?
Yeah, molded into solid objects. That's the defining characteristic. They're all polymers, basically long chains of molecules.
And the specific chain determines the plastic type.
You got it. Leads to all the different properties.
Okay, types mentioned are PVC, polymer resin, which is kind of general, thermoplastics, and thermosetting plastics. Let's start with PVC. Polyvinyl chloride. Pipes, right?
Pipes are a big one, yeah. That's the rigid form, RPVC.
Yeah.
Used in construction a lot. Pipes, window frames, door profiles.
But there's a flexible kind, too.
Mm-hmm. Add plasticizers and you get flexible PVC. Used for, all sorts of things. Bottles, packaging, done not usually for food. Bank cards, membership cards, that sort of stuff.
Wow. So the same basic plastic can be hard like a pipe or flexible like a credit card?
Depends on the additives and processing. Very versatile.
Okay. Now, thermoplastics versus thermosetting plastics. This sounds like it's all about heat.
That's the absolute key difference, yes. Thermoplastics, sometimes called thermosoftening plastics. They get soft, moldable when you heat them above a certain temperature. Then they harden when they cool down.
And you can do that again and again.
Pretty much, yeah. Like butter, as the analogy goes. Melt, solidify, melt again. It doesn't fundamentally change the chemical structure much.
So things like polyethylene, like in milk jugs or plastic bags.
Exactly. Polyethylene, polypropylene. Lots of common ones are thermoplastics. That's why they're often recyclable.
Ah, okay. Because you can melt them down and reshape them.
Precisely. Now, thermosetting plastics, or thermosets,
Yeah.
they're different.
How so?
They might start as liquid or malleable, but when you heat them, they undergo an irreversible chemical change.
Irreversible.
Yeah. Strong cross-links form between the polymer chains. It cures them, sets them permanently hard. You can't remelt the thermoset.
So once it's shaped and hardened, that's it forever.
That's it. Think of like epoxy resin or Bakelite, the old plastic. Once cured, heating it will just cause it to char or degrade, not melt.
Okay, that's a really fundamental difference in behavior. Heat makes one reusable, heat sets the other one permanently.
You've got it. Big implications for manufacturing and recycling.
Which brings us, inevitably, I guess, to the environmental side of things. Plastics.
Yeah.
Burning, disposal, pollution.
Yeah, it's a huge issue. The source talks about plastic pollution, just the accumulation of plastic waste in the environment.
And it harms wildlife plants.
Absolutely. Animals get tangled, they eat it, it messes up habitats. Plus, the source notes 2 big underlying problems.
Okay.
Okay.
1, many plastics are made from compounds that can be toxic, and these might leach out over time.
Right.
And 2, the very thing that makes them useful, their durability, means they just don't break down easily. They're not biodegradable.
They just hang around forever.
For incredibly long times, yeah. They might break into smaller pieces, microplastics, but they don't really disappear. And those microplastics get everywhere. Food chain, water, soil.
That's pretty sobering. The durability is both a blessing and a curse.
It really is a major challenge.
Okay, so we've journeyed from like plywood layers all the way to the chemistry of thermosets and the problems of plastic waste. Looking back, what are the main things you think people should take away?
Well, I think just the sheer variety and specificity. You know, with boards, seeing how we manipulate wood, layering it, breaking it down, pressing it to get exactly the properties needed, strength, density, weight.
Yeah, engineering solutions from a natural material. Right. And with plastics, that core difference between thermoplastics you can remelt and thermosets you can't. That explains so much about how they're used and the recycling challenges.
And the environmental impact hanging over the plastic side, especially.
Definitely. That durability issue is critical. It drives a lot of research into new materials and better ways to handle the waste.
Absolutely. It's easy to just, see a wall as a wall or a bottle as a bottle. But there's so much material science packed into these everyday things. Hopefully we've shed a bit of light on that.
Hopefully.
So considering all that, the strength from layering plywood, the way thermoplastics can be reshaped, the toughness of cement board, but also the challenge of plastic persistence. Here's a final thought to leave you with. Imagine if we could really get down to the molecular level. What if we could borrow and blend the best bits of these different materials? Could we design completely new building materials? Maybe ones that have the strength, the moldability, and somehow solve the disposal problem. Like materials that perform brilliantly, but then, I don't know, break down safely when needed.
That's the dream, isn't it? Molecular level design for function and end of life.
A fascinating thought anyway. Thanks.